Assalamualaikum. Okay, guys. Okay, let's start. All right. So actually, we were discussing for past couple of weeks the wind design and wind-induced loadings on our structure, and how to calculate the wind loads on our structure for different scenarios and different conditions. So one thing was left was the torsional loads. Okay, how the torsional loads come, and then how as a structural engineer we need to understand the analysis to resist the torsion load, and also okay, how the loads are being generated by using the ASCE 716. And actually, when I looked into an ASCE 722 which just came out, it's not been adopted yet. It's all the jurisdiction at the moment at national level, they are following the ASCE 716. From most probably AC 722 will be adopted in pretty soon. As soon as the new version of the code come IBC new version, so that definitely it would refer the AC 722. So then we will have to follow the AC 722. There are some changes, but the fundamentally in the entire wind chapter, in the entire wind design concept. Okay, let me phrase again. In the entire wind design concept, all the concepts are exactly same. There is no theoretically there is no difference. Okay, if you understand the AC 716 wind induced loading, then you will be able to calculate the pressures by using or utilizing ACE 722. That's why just by hand I put it like AC 722. So the topic which were left for us to cover in all past sessions was the figure 27.3-8, actually, which is in the chapter 27 of ACE 716, and the heading is the wind torsional loading. So let's start. So this is the chart which is actually has been taken from the AC 716. And as you are aware, the chart, the figure is 27.3-8. If you go to figure 27.3-8, you will see all these four cases. Okay. And this you must understand first. Okay, you have to have the proper understanding okay, how to use these cases, how to generate the load combos, and then once you have the load combos, and then how to utilize your wind loading on your structure. So you need to have the proper understanding. So far we have covered AC 76 wind chapter, AC 716. So like general requirements in chapter 26, we covered fundamentals of it. Then we covered chapter 27, wind loading on buildings, main wind force resisting system. Main wind force resisting system. Always remember, for your main lateral system for any structure, doesn't matter. It is like if it is residential structure, if it is commercial structure, it is utility structure, or it is industrial structure, doesn't matter. Whenever you will talk about the main lateral system, then you have to go back to the code for the main wind force resisting system. Okay, because that's the main skeleton, main lateral stiffness you have over there, right? You will never go for CNC pressure. CNC pressure is for the components and cladding. Okay, whenever you will design the wind girds or you will design the roof purlins, then you will take the CNC pressures. You will calculate, you will develop the CNC pressures, then you will get your uplift forces on the either the roof or on the wall of the structures, then you will apply the CNC pressures. Okay, but whenever we will discuss the main lateral system of the building, then we must have to go to these chapters and then see which chapter is applicable, and then how you can calculate the main wind force resisting system pressures. Okay, so these are the like fundamental guidelines. So these guidelines will just tell you which type of structure you have, what occupancy you have, what kind of topographic factor you have, what kind of like all the factors which we have so far discussed in kind of like detail. Some of them in brief detail, some of them much more like required details. All right, so we covered 26, chapter number 26, 27, then 28, then 29, then 30, and 30, yes, commercial cladding we already covered. Chapter number 31. Chapter number 31, always remember, this is like what I have seen so far in my experience. It is like very unique structures. like kind of like heavy utility structures. If you're doing the power plant in a let's say South America, right? The wind speed, it at service level, the wind speed is like 160, 170 miles an hour. So then probably, and it is critical structure, power plant, right? It has to stay for the next 100 years, right? And then it has to be operational. So you really want to see the exact pressures. So then you would request the client, okay, okay, we would like to get the wind tunnel pressures. Actually, the high-rise buildings, just like Burj Al Khalifa, Burj Dubai, Burj Jeddah. So those are the structures we would prefer. Okay, by following the code, we will follow the code by concept, by design, but we will see the actual exact amount of pressures at the different elevations of the structure. Okay, so then we will go the wind tunnel method. Okay, and but the main question after calculating these pressures, okay, are you in complete compliance of the code? So technically speaking, once you have all, you take the structure and then you develop your pressures, then you have to develop your load combinations, right? So we have so these load combinations. So in order to understand these load combinations, you have to imply, and you have to imply the torsional loading also. Okay, so in order to understand the torsional loading, then we have to go back again to the code, which is 27.3-8, right? So let's come here. What AC7, and let me tell you one more thing. 702 has this, but not that much applicable at that time. But 705, when it came, the AC 705, it came very strong. Okay, you have to include this, the torsional loading. And remember that torsional loading, technically speaking, it is more applicable for the rigid kind of like diaphragm, which we discussed before. Okay, flexible diaphragm, rigid diaphragm, right? Usually when you have the wood deck like advent deck and the roof joist and the roof trusses, so usually it is the flexible diaphragm based on the practice, right? Otherwise there is empirical equation in the code that your overall lateral displacement has to be less than the average, so then it becomes a flexible diaphragm or it is the rigid diaphragm. But torsional loads, when we talk about the torsional load, it has to be the rigid diaphragm. Okay, it has to be the rigid diaphragm. It is not applicable for the flexible diaphragm. So flexible diaphragm, so you guys have been doing a lot of like residential structures, townhomes kind of thing. So residential structures and townhomes, what is the mean roof height? Usually for the residential structure, 35 to 36 feet roof mean height, right? Townhomes also the same thing. Okay, they are usually 40, 41 or 42 feet, right? So these structures are not prone to the torsional loading as required by the code. Code required the torsional loading is torsional loading on every single structure, but these two structures do they qualify for the torsional loading? No, they don't qualify for the torsional. In order to qualify for the torsional loading, you have to have concrete building. Let's say yes, then it is going to see the torsional loading because you have the rigid plate, and then there is a problem. Okay, you're gonna see the torsional loading and torsional stress in your structure. Okay. All right, let's move forward. So what is torsion? This is same basic. Okay, you have the twisting. When the wind blows on your structure, then it will try to twist from which this leads to, okay, in structural engineering mechanics, torsion occurs when an external force causes a structural element such as beam, shaft, or column to rotate about its longitudinal axis. This is a very wonderful, this is a wonderful picture. So just for you to like imagine to what the torsion can do with your structure. It will, like, it is exaggerating. Of course, this is amplifying, and just like it does not happen that way, but it's just to give you the visual grip. Okay, what exactly is going to happen with your structure if you don't design for the torsional loading? Okay, so this is the torsion, and why it comes? What is the concept? The concept is, as we discussed before, you have a rigid diaphragm, right? So your diaphragm is like kind of like fixed here, connected with the elements below, and then connected here with the elements below, connected here with the elements below, right? You apply the load. As soon as you apply the load, what happens? The structure already has one center of mass, right? But your center of rigidity That's called the inherent rigid, but default is eccentricity in the system, right? What is the default eccentricity? The building's building center of rigidity, CR, is a point through which the resultant of all the resisting forces acts. That's a CR, right? And CM is a center of mass. So eccentricity is like essentially has to be the offset between these 2 points. And every single structure, let me tell you, even though we do not consider the eccentricity, we do not consider the eccentric the moment produced by the default eccentricity, but when you calculate in the when you run the analysis in the software is already doing it. Okay, it's you to verify whether how much by default eccentricity you are going to have it. Let me give you like simple, okay, why it happens in a like very ordinary or straightforward like symmetrical structure. You always have, see, whenever you have the like 5-story 6-story building, you have the openings for the stairs, you have the openings for your, what do you call it, for your elevator shaft, for your or for some other purposes, right? We sometimes we have the big chases, right? All the ducting, cabling, all the piping, critical piping is going through those going through that opening. So that introduces the unsymmetrical unsymmetrical situation in the entire plate. So CM somewhere here and CR somewhere here. So whenever this situation occurs in any diaphragm, and it has to be rigid diaphragm, right? Flexible diaphragm, no, it does not apply. Why the flexible diaphragm it does not apply? Because it's like a simply supported beam. It's like a simply supported deep beam, the flexible diaphragm. But the rigid diaphragm is exactly opposite to it. Okay, so whenever you have this kind of this is the openings. Because of the openings, we have this situation. But why? But still, if let's see if we do not have the openings, so what code is saying? Code is saying, let's say if everything is so perfect, symmetrical, everything is perfect. So code is saying I have the CR and then I have the CM is right here. CR and CM coincides. Code is saying no, is still you will consider the 15% eccentricity for the wind and like 5% eccentricity for the seismic. So it's still the code says whenever you have this situation, everything is symmetrical, you have this this offset. Always you will have this offset. Make sense? Okay, you will have this E between these two main centers of the structure. So this is the center of the stiffness, center of the rigidity, and this is center of the mass. Okay. Code is saying you have to add it. That's why the people started calling it, even the code using the nomenclature as the accidental eccentricity. So when you will go through the seismic provisions in the code, so you will see this word, the accidental eccentricity. So even for the wind, we can assume it same nomenclature can be applied for it. Okay, so it can be called as the accidental eccentricity. In wind, it is 15%, and in seismic, it is 5%. Okay, inshallah, when we'll start the seismic sessions, then you will see how much critical this concept is. Okay, and then why it is happening. It is the fundamental concept. There is always the center of mass and center of rigidity does not they never coincide. They never coincide. Okay, even in a symmetrical structure, they never coincide. Code is saying okay, whatever the by default eccentricity is coming from by your analysis, you have to add on top of that. This accidental eccentricity. Makes sense? That is already being that is already being calculated by the whatever the software you are doing it. If you are doing the hand analysis, then you have to calculate by yourself. Okay, you have to calc out by hand what is the natural eccentricity. That's called natural eccentricity in your structure, and this is called accidental eccentricity. So wind torsion, when we say okay, this whenever we discuss this, so we discuss case 1, case 2, case 3, case 4. So actually we discuss this 1.5 Bx or 1.5 By. We are saying accidental eccentricity is being added to the natural eccentricity which is already there in the system. Makes sense? Conceptual it's so simple. There is nothing which is special or it's not the rocket science. Okay, the code is saying whenever you are analyzing the rigid structures, you have to introduce in your structural system, you have to design your lateral resisting system, lateral load resisting system. You need to design for the torsion loading. That torsion loading is coming primarily because of the just one reason, main one reason. That's the natural eccentricity in the system because of the offsetting of CR from the CM. On top of that, code is making you liable to add on top of that the eccentricity, the accidental eccentricity to the natural eccentricity of the system. Okay. And how this is like okay, so this is not only in one direction, right? So just like we have seen, okay, in this direction this is eccentric, so in this direction also it is eccentric, right? So, and then the final kind of like to in order to understand on both axes, okay, what's going to happen, okay, the CM and CR, so we will have this kind of like in order to understand the pictorial view, or just in order to feel it, okay, how the torsion is coming on my rigid diaphragm, and then how these reactions will be generated at the corner of the structure, so, or wherever you have the your lateral system. So because it has to resist, it's a lateral load, so lateral load has to be resisted by the lateral system, right? That lateral load resisting system, either it is shear wall, either it is your bracing, or your moment frames, whatever it is, or it is combined, or both of them. So this slide will give you the fundamental basic idea, okay, how these loads are being like generated in your system, in your structural system. Let's move forward. And remember that one more thing. So load combinations, you generate the load combination. So you have this structure, and you have the north sign up. So this is north south loading, okay, and this is NSEW. So this is east west loading. But remember one thing, this is extremely important. Okay, these loads you are generating, again, see, I'm repeating again and again because I have seen the mistakes again and again, so that's why I'm trying to tell you, if these loads, whatever the loads you are generating right here, you are generating the load for the main lateral system of the structure. Okay, shear wall right here, shear wall is right there, shear wall is right here, shear wall is right there. Always remember, whenever you try to understand a concept, you have to understand from the fundamentals, basic, so that because your neurons will remember it for the rest of your life. If you try to understand or try to memorize it, or you try to keep in your memory for the longer period of time, you need to understand from the fundamentals and simple basic. You are Einstein, but not everyone is an Einstein, right? So you have to make it simple in order to understand. So this is like simple rigid diaphragm kind of building. You have the shear walls, so lateral load resisting system at the periphery of the building. And then if I apply the load from here, so this is south to north. If I apply load from here, this is north to south. It's from here east to west, west to east. So this will be these pressures, only wind force resisting system pressures, which you by now you already know, and you are the expert how to calculate these wind pressures for the MWFRS system for any structure you are designing. Okay, because by the law you are required you have to follow the code. Okay, the only topic which is left is the torsion load, so which we are covering right now. But what code says? Code says, okay, when you apply the load, okay, so okay, hold on, give me a second, just a second. See, these loads are at ultimate. These loads are not at service level. When you generate the load, when you apply the load, so this will be from wind from west to east, okay, and if you apply the load from here, south to north, but at ultimate level. Remember that still 705 the wind used to be at service level, but from 710 onwards until today 722 it's not at service level. If you're designing the structure, let's say you're designing the post tension concrete, has to be at service level. If you're designing composite structure has to be at the service level, because you can design LR based on the LRFD, but I have been doing all over the globe. I have designed the heavy utility structures. I have been designing the power plants anywhere, Europe, Middle East, Asia, South Asia, Far East, South America, you name it. Even the power plants in Australia, I used because it was the requirement by the client. It has to be you have to follow the ASD, allowable stress design method. Okay, so so I said PT, post tension concrete. I said composite structure. I said the, what do you call it, steel structure. I said CFS. I'm saying CFS. I'm saying smart material, smart material structure. That those are the specific materials which you are using in your furnace support structures. Those are the smart material structures, right? And all of them is still today, 2025. I'm talking to you. 2025, we use ASD, allowable stress design method. Okay, only concrete and conventional concrete. Remember my words. Only concrete, conventional concrete is being designed at LRFD, not PT. Okay, and not unconventional concrete. I'll explain what does it mean, what I'm saying to you. Okay, so you need to, the LRFD, you already know it extremely well, but you need to know the ASD also. Okay, how, what is the design philosophy, and then how these concepts are being applied on your structural system and on your structural elements of the structure. Okay, so the load combinations you are seeing right here, these are at ASD level, but the wind which is coming from here, it's not ASD level. So what you will do, we have learned before, okay, when you calculate the loads from the code for the wind pressures, when you calculate total wind pressure, how you will calculate total wind load, how you will calculate it. It's simple, pressure times surface area and whatever the load is coming, right? You will take that load, you will multiply by 0.7, that will go, that the load will come at the service level. All right, you got it, all of you. So this will make this load at service level. Once the load comes to the service level, then you can plug in that value right here. Now what code is it? This figure, so if you come to here, case, it was, see here, pay attention. Case 3, what case 3 is saying? Case 3 is saying, you will apply my brace or my shear wall right here. It has to be designed. It has to be designed for the wind which is being applied from here. But remember that if which wind we are talking about? We are talking about the main wind force resisting system plus which direction I'm applying the wind pressure, right? So this is not the wind which is coming from here. No. The wind you will take from here. Then you will add these two winds, okay? And then you will take the wind which, whatever the wind is coming from that direction, windward, leeward, then windward, leeward, then you will add algebraically, you will add these two, and then you will design your shear wall right here. Make sense what I'm saying? It is the same concept. It is the same concept in seismic loading also. Seismic, how you calculate the worst loading effect on your lateral system or lateral the lateral, like any lateral system in your in your entire structure, right? Okay, you take 100% from here, you take whatever the load is coming, you take 30% from there. That's for seismic. But for AC 716, AC 722 is saying the same, exactly same thing. You take 0.75 windward leeward combined, then 0.75 windward leeward combined, then you will design this shear wall, then you will design this shear wall, then you will design this shear wall or this shear wall. Make sense what I'm saying? Okay, and you can see it right here. Okay, how the cases are being, you take 0.75, the pressure from one direction, the pressure from the other direction, and this we're going to discuss just in a bit. Okay, so this is what, if you understand this case, or like this case, how the pressures from the different orthogonal planes or orthogonal faces, see the direction under consideration, that's your main direction, you will take 0.75. Then the direction which is the perpendicular to the direction which is under consideration, you will also take 0.75 from there. Make sense what I'm saying? Okay, come to here. So if you see here, you see, you will take the dead load, whatever the dead load, that's called minimum gravity load. Okay, minimum gravity load to resist the uplift. Let's what we used to discuss 0.6D and 0.6D plus 0.6 wind. So this is what it is actually. This is coming from here, from AC 716. So what AC 716 is saying, case 3, look at this. 0.75 wind load, north south direction. North south direction. This includes the windward and leeward total pressure times 0.75 plus 0.75. Let me delete this. Plus 0.75 from the other direction, which is the perpendicular direction. Makes sense what I'm saying? Okay, then you are considering the worst possible effect of your wind on your lateral system. Okay, worst possible. So this is 0.75 right here, 0.75 right. Then this is, of course, then you're going to change from all the directions. Okay, this is for case 3. Makes sense? I am designing this bracing, or I'm designing this moment frame, whatever the rigid frame you have, whatever the lateral system you have. Okay, but this has to, let's assume that you do not have the shear wall anywhere. You have the shear wall right in the middle. Let's see, this is the shear wall right here, right? Just assumption, right? And this is the rigid diaphragm. This shear wall must resist. This is the minimum, must resist, because this shear wall is going to see the excellent uplift, because if you're going to combine from the both direction, so obviously the uplift going to increase, right? It's not going to increase from the one direction. Whatever the uplift you are getting, and actually is higher if you combine both of them. Okay, so this shear wall going to see the 0.75 the wind pressure from here, and 0.75 wind pressure from there. Then again 0.75 from here, then a 0.75 from there. Okay, so you have to run all the load you need to develop all the load combos like this, and then analyze your shear wall. Then your structure will be in compliance with the AC 716 and AC 722. This is called this is called the compliance of the shear wall design under the case 3 of AC 722. Okay, makes sense what I'm saying? So the same thing for case 4, figure 27.3. Case 4, figure 27.3. Go back to your main. This is the main body, case 4. Okay, so what code is saying? 0.563 windward leeward combined. Then you have to same thing. If you pay attention, 0.563, then you combine both of them. We're going to discuss the eccentricity and that load, and then 0.563, then the load from both direction, then eccentricity, then it will be the full load combination for this case if you have a shear wall right here. So then the code says, okay, then you are in the compliance with the AC 722. Okay, makes sense? But this is not for the flexible diaphragm. This is not for the residential structure. This is not for the townhomes. This is not even for the structures which we usually design, like low rise kind of structure, like 40 feet, 50 feet. No. Yes, for backlay, yes. For the silo, for any industrial structure, we always do it. This is the standard practice. Okay, this is the standard practice. Someone can come and argue with us for, let's say, four-story building, CFS building. The guys, you have been doing a CFS, some of you have been doing the CFS building. Yes, someone can come and argue with us, okay, why you are not considering the torsion load. But there is another reason, because those we designed for the 2-hour fire rated shear walls, and then the concept is okay, one breaks down, the diaphragm is disconnected, and the rest of the structure will stay. So that's why we have the shear walls in every single unit, right? You are understanding what I'm trying to say. So in that case, we don't have, that's why I never apply these loads over there. Why to overkill it? Okay, so it's actually being an EOR, being a lead designer of the project. It is you to understand and apply all the code provisions on your structural design. Being the EOR stands for engineer of record. Whoever is the engineer of record of the structure, because he's taking the liability of the entire structural system, right? He's going to perform for the first load, whatever the first load effects come to his structure, right? So it is his responsibility to understand the code first, which we have been doing it for past several months now, and to understand the codes and apply all the code code clauses, code, whatever the code requirements are on the structure. But there is a possibility that you understand something, but you feel that no, your structure does not, matlab it's not. There is no need for like residential structure. It usually comes under the IRC, but the townhomes come under the IBC, right? But still we don't apply it. Why? Because we know it's not, it's anything 40 even up to 50 is not. But industrial structure, let's say the silo come for just like 40 feet height, we must apply these application, we must apply these clauses of the code. We must have to calculate, because the code is very like is kind of like stringent. Your code is very restricted. You have to consider all all the possibilities of the worst load combinations or the worst load effects on your structural system, right? So then we obviously we will apply it. Okay, it doesn't matter what is the height of the structure. Okay, but the primary difference which I've been like keep telling you, okay, it's always remember, on the flexible diaphragm there is no torsion load, on the rigid diaphragm there is torsion load. But even in the rigid diaphragm, where you don't apply, usually townhomes projects you don't apply, usually like ground 25 feet, 30 feet or 35 feet steel buildings you don't apply, or even 30 to 40 feet concrete buildings, tilt wall buildings you don't apply, right? But some engineers, they do not take the risk, and they say, you know what, no, I would like to apply these cases, case 1, case 2, case 3 from the ASCE, and then so that my structure should be in compliance with the ASCE 7. So there will be no kind of like what do you call it, there will be no ambiguity left for others to like start questioning or getting like doubts in their minds, oh, something is going to happen. No, it's not. It's the actually it's always you are the main person. You are the structural engineer, you are the lead designer of the project. It's you to take a decision. Okay, how you gonna apply all these provisions on your structure, and up to what level. But like I said, I explain in detail the type of work which we have been doing past several years, where we will apply and where we will not apply. Okay, type of building in Pakistan, type of buildings in Middle East, like you most of the time PT plate, and then concrete columns, all the way up is concrete, like 6, 7, 8 story. They must have to apply all these provisions on their during the wind analysis of the structure. Okay, they must have to apply. Okay, there is no way the wind not going to produce the torsion on those structure. It's impossible. Okay, whatever the after tornado or after destruction we have seen it. Okay, we have seen the problems over there. So those kind of structure which are which 100%, these are the rigid structures, 6, 7 story structure. So they must have to apply these provisions. Okay. All right, so next is the load combination. Okay, so these load combinations, so we kind of like test based the direction, then we test base case 3, then we test base case 4, and then here you understand how this wind torsion is being calculated. Okay, oh, one more important thing is still the industrial structure, because I'm very much comfortable with this 0.6D plus wind load. Because the till AC 702, AC AC 798, 702, 705, the wind loading was at service level. So this was the best load combination for us to calculate the uplift at the base of the column, right? Or wherever we wanted to get it. So at that time, this 0.6D plus wind load was at a service level, but now the wind is at the ultimate level. So what AC 716 and also 722 indicates 0.6 dead load plus 0.6 wind. Why they are doing this? Because they are bringing back to the service level, because this is at service level, right? Makes sense now? Okay, why some of you asked me this question before? Okay, this is 0.60 and then a wind is also 0.60, because the wind is the pressures you are getting right now from AC 722 is not at service level, it is at the ultimate level. So that's why you have to bring it down to the service level, 0.60 plus 0.6 wind. Okay, and but if you want to use this load combination, which is the favorite load combination, especially in industrial structures, this is because define this as the minimum gravity load to resist my uplift, and this is the wind load. So it has to be at the service level, like we discussed before on the previous slide. Okay, whatever the load you calculate, and if you are doing the ASD design, you have to multiply all those primary load combinations. Those are called the primary. These are called the primary load combinations. Okay, these are called the primary load combinations. Okay, these are the all primary load combo. Okay, and this has to be multiplied by 0.7. So then you can use all the load combinations you have for the ASD in your analysis. Then you can use these like with the comfortable heart. Okay. For LRFD is different. These are completely different. But the type of structures usually at the global level, it's all ASD. This is interesting. So only conventional concrete is done with the LRFD. All right. So this is one of the diaphragm. This was, we discussed, this was a steel structure. This is the metal deck. So this was, this is the roof, and kind of like semi-flexible, not 100% flexible. So we calculated the pressures. First, we calculated the pressure, as we discussed so many times, how we calculate. And these the pressures were calculated for MWFRS, main wind force resisting system. So we have one rigid frame here, we have one rigid frame here, when we have one rigid frame here, we have one rigid frame here, we have one rigid frame here. So when my lateral load will come, so the load will go through the diaphragm, which is at the roof. This is a diaphragm, right? And then it will the load how the lateral loads will be resisted, because we have the lateral stiffness at these rigid frames. My grid line 1, grid line 2, grid line 3, grid line 4, because these are the moment frames. Okay, that's why these are the rigid frames. Okay. So you calculate the loads. How you calculate the loads, we discussed before. I just want to show this slide. Given calculations, wind pressure calculations per AC 7. It is AC 7, and now it is 22 also. Okay, so AC 716 and AC 722. So wind direction, then wind velocity, building category, risk category, exposure category, topographic factor, K sub ZT, salinity factor, whatever the direction you are in considering, like a K sub D, top of pyramid, velocity, wind pressure, and then you will calculate the velocity pressure in PSF. Then we use 90 PSF over here. Then you calculate your wind parapet, wind leeward, and then C sub P. We already discussed in so detailed. You should have at least the fundamental concept how we are getting all these values from the code. Okay, so and then you can see all the code sections and code referencing also. So you can go back while you are watching this video, then you can go back and check in AC 716K. Actually in the AC 722, these are also the same. The chapters are same, 26, 27, 28, 29, 30, and 31. So that these are obviously essentially is going to stay the same. All right. So you calculate your wind pressure. Then once you calculate the pressure, surface area, and then okay, height of the building divided by 2, and this is the height of the parapet. So pressure is this. So this is my roof, this is my parapet, and this is the wind pressure. Okay, makes sense. And then you calculate the total pressure, because this is the level where the load gonna go, because this is your diaphragm, right? Your rigid diaphragm. So we calculate how much wind will come here, what will be the, and it is just that based on the tributary area. Okay, this is simple, straightforward, just to make it simple. Okay, otherwise when you use the STAD or RAM or adapt, whatever the applications you are using, they generate the pressure, but the problem is that you got to check everything by hand if those pressures are correct. Okay, otherwise your wind shear at the base will not make any sense. All right. So you calculate that, and then once you calculate the pressures and stuff, so you can see, okay, wall pressure, windward plus leeward, 19 PSF, parapet pressure, 48 PSF, roof uplift, BY and BX. What is BY and BX in this case? See, 82, my BY 39.5 and BX 82.5. So this is 82.5. So this dimension is actually your B sub X, and BY, this is the dimension you are considering. Okay, and let me once again where it is. Okay, see here. You see this is Bx. See? Okay. Okay, how you calculate the concentrated load? This dimension times the pressure, and then whatever the height. Okay, and then this is By. All right. Then come back here, and you are trying to calculate the torsion on the structure. So By, Bx, width of the building perpendicular to the wind direction, either B sub x or B sub y, and similarly E sub x or E sub y, eccentricity for the both eccentricities. Okay, either is in this direction or the other direction, which has to be orthogonal or perpendicular. Okay, eccentricity for the x and y principal axis of the structure respectively. Solution. So you just plug in the number, you will get eccentricity, and then how you will calculate the torsion according to AC 716 or AC 722. Figure 27.3-8 case 2. So this is the equation you're going to use, and then once you use it, so you will end up calculating the total force 35.616, and then multiply that force to this eccentricity which you calculated right here. This is your eccentricity, and then we are doing just one direction just to make it simple, easy, so that it will always stay and exist in your memory for the longer period of time, inshallah. Okay, and then so how much torsion is coming on your diaphragm? 441 cubic feet. Okay, and then you will resolve this diaphragm into the equal couple. So what is this is, you see this, okay, what number you got? You got like 5.342 kips, and then you divide by 2, and then this is like 2.67 kip right here, and then 2.67 right here. So this will try to turn this way. Okay, this has to be added. This has to be added. Where? This has to be added, because once you define, see, this you have to calculate by hand. This is what I usually so that you can understand. First of all, you understand, and you can cross check. You got to run the sanity checks, whatever the results you are getting from the application, whether it is ETAP, SAPS, STAT, RAM, PT, RAM concept, RAM steel, RAM advanced, all these softwares, none of the software is accurate, none of the software is correct until you check it by yourself. You get the satisfaction within yourself, and then you satisfy yourself, okay, this is the pressure I calculated by hand, and this is the pressure the software is calculating. Then it is correct. Then you calculate the wind torque on your structure, and then you check it, and then at the base, if the base shear is making sense and matching with your sanity checks and hand calc out runs, so then it is making sense. Otherwise, nothing is right. Literally, otherwise nothing is right. Modeling is nothing. It has to make sense. You have to feel accurate. You have to feel confident. You have to feel satisfied. Okay, whatever is coming is right. Okay, whatever is coming is right. Make sense what I'm saying? So you get these values and then go back to the load combination. You remember that? So load combinations, we have something over here. See this WT, what it says? It says load. Let's just don't go to nomenclature. Go with the concept. What is the philosophy? So this is the minimum gravity. Okay, minimum gravity load which gonna resist the uplift. Take then 0.75 wind load north south. 0.75 wind load north south, but the torque which is coming from this load combination. Makes sense? See, so you have four primary load directions: north south, south north, east west, west east. Four. Okay, so these four you have to calculate the four different directions of four different moments on the same diaphragm, and you will apply, and you will make, this is just the concept, but you will generate the same. But if you see this concept, if you understand this, then you will get it. Okay, how? So this is going to be added. So you will change this north south primary load, north south wind torque, south north primary load, south north wind torque, east west primary load, east west wind torque, west east primary load, west east wind torque. Makes sense? Okay, then you will use it, and then you will apply it. And then the next load combo, load combo, exactly the same thing. What is that? 0.75 wind load north south. Then you will add 0.75 wind load east west. Then one time you will take the wind torque from one direction, then the next time you will take the wind torque from the other direction. Make sense? Okay, like this way. Excuse me. You have this structure, right? You solve from both direction. Whatever you design your shear wall for the wind pressure from this direction and wind pressure from this direction, but you don't know how you will get the worst uplift. So you have to add the wind torque with this load combination. So there will be 4 wind torque. One wind torque is coming from this direction. One wind torque is coming from, so one wind torque is coming from this direction. Okay, one wind torque is coming from this direction, one wind torque is coming from this direction, and one wind torque is coming from this direction. Why it happens? Why? Okay, and this is the intent of the code, seriously, the way we understood it. Okay, why? Okay, I just showed it like one load combo here just to make it sense to you. Okay, how this because they realized the intention of the code is you design for the worst possible load effect on your structural element, okay, within your structural system. All right, if you understand, if you follow this sentence, so you will see wind is hitting, see, my wind is hitting this direction, then wind can, and at the same time you are taking the effect from this direction also, same time wind can go and then can hit at this corner, right? So you will have some kind of pressure here, right? Okay, this is the centroid and this is my CN, so there will be some torque. Okay, then the same wind is still hitting right here. I'm not talking about the side pressure, I'm not talking about the uplift, I'm just talking about the torsion, nothing else. I'm just talking about the wind induced torsion on my diaphragm or on my structure. Okay, so it can go and then hit from here. Okay, so, or it can come and hit from here, because it is, see, it's not like seismic. Wind is completely different. Wind is completely unpredictable. That's why code is so stringent. Because why I'm saying this, because we have seen a significant difference between the wind tunnel pressures when we do the power plants and we request the wind tunnel pressures, and whenever the same height of the building we try to develop the pressures by the ACE 7, and then we see, oh wow, why these pressures are so high, because the code wants to be on the, I should not use this word, code wants to be on the conservative side, right? So these pressures are already on the higher side. Plus, then all possible faces of the structure, all possible directions of the hit, the code is considering. That's why if you follow AC 7 wind concept, then your structure 100% will be saved and will be stable and strong enough to resist any kind of wind for the intended wind pressure, right? So does it make sense? Okay, why I'm saying, okay, you take the load, the pressure in one direction, then you will add one combo, one load combo, this direction wind torque, other combo, this direction wind torque, then the third combo, this direction wind torque, then the fourth combo, this direction wind torque, right? And then you have to develop all these load combinations. I did not put all the load combinations right here, but as you can see, like see 120 and 130, you see, okay, 138, you see something over here, you see this, yeah, how this is, okay, 0.6, that this is the minimum gravity load, okay, after the reduction, 0.75 wind load west east, 0.75 wind load south north, and now you see it. Okay, but then you have to then understand also which one is going to be added and which one is going to be subtracted. So see, okay, one time is being added and one time is being subtracted. So there are, again, it's a complete matrix. Okay, I'll send you the whole either in the Excel sheet or in the what do you call it, or in the text form, all the load combinations, okay, when you're going to add and when you're going to subtract. So you can see that in the next load combo, okay, we are considering, so this kind of like the worst load combos, okay, when you apply on the structure, especially for utility structures, industrial structures, or low rise, or the mid rise to high rise buildings, okay, 0.75 wind in west east, 0.75 wind in the south north. So actually you combine both of them, right, from both directions.
which are like orthogonal to each other or perpendicular to each other. Then you add the wind torque. One time you're adding and one time you're subtracting. Okay. Does it make sense what I'm saying? Okay, you are taking the worst possible load effect on your structural system. All right. Okay, you are taking you are combining the wind pressure from wind loading from two directions, and then you are also taking the worst effect of the wind torque from those two load combinations. Okay. See here, wind west to east, wind torque west to east, wind load from south to north, wind torque from south to north. Okay. And I'll you know what, this is not the intent here to discuss all like 200 load combinations based on this all the wind load combinations. I just wanted to touch base just to give an idea. And so if you are interested, I'll email you the complete load matrix developed for wind loading under the understanding and influence of ASCE7. Okay. And then you will see what exactly we are then you will see how the one time it is added, one time it is subtracted, and it is easy. It's not that much difficult. Okay, the last thing I really want to show you, because I asked you guys, I think I asked someone. So okay, does the ETABS does consider it? Yes, ETABS does consider it. But again, I would like to request all of you, whenever you solve any structural system, or whenever you run the analysis for any structure in ETABS, at the base or from the beginning, from the pressures, go all the way down. You have the reactions at the base, and then start checking those reactions. Because see, if you have this concept and then you are running the sanity checks, you got to run the sanity checks. If you don't run the sanity checks, and there are major problems we have seen in the field. Okay, the guys are running the analysis through using the computer, and then they do not understand what the results are coming, and they just like they give those results to the draftman develop the drawings went to the site, and that's it. So, and then we were like, oh wow. So this is like, you got to make sure you got to run whenever. This is very critical and in general advice to anyone who is listening to this this session, that whatever the results you get from any software on this planet, you got to run the sanity checks by yourself. You got to run the hand calc. You got to calc out by yourself, so that you make sure whatever is coming is correct and accurate. I hope this is good. Now this is the time for the question and answer. Let me stop recording, and then we can go to the question and answer session. All right, guys, you can go ahead one by one, whatever your questions and doubts. And thank you very much for watching this session. Thanks. Bye.